This is EC 201, lecture 44. So the last time around, we were investigating the stability of a negative feedback system with a third order forward amplifier. And we found that the loop gain A or S of F for the third order system is of the form some A naught F divided by 1 plus S by omega P the whole cube, where the fact that all the three poles are at the same place is not particularly restrictive, serves to illustrate a point. And what did we say? This we called the loop gain function, and we realized that the V out by V in as a function of j omega is of the form 1 over F times this loop gain of j omega divided by 1 plus loop gain of j omega. And we saw that if the forward amplifier characteristic is like this, then the closed loop system becomes unstable for A naught F greater than or equal to 8. The whole idea behind going to a 3-stage forward amplifier is to make A naught as large as possible, preferably in the tens of thousands. Now, this is a problem. What did we say? We said that if we somehow make the third order system look like a first order system, then closed loop stability can be obtained. And the motivation for this line of thought was that we saw in our earlier arguments that a first order system is unconditionally stable. So if we somehow make this three-pole system look like a first order system, then the closed loop system hopefully will be stable, just like in the first order case. And how do you make the third order system look like a first order system? One way of doing that is to cascade along with this system another pole which we denoted by omega sub d, and if omega d is much smaller than omega p1, then it is possible to make the frequency response of this chap resemble the frequency response of the corresponding first order system, which is 1 plus s by omega d, over a wide frequency range. Does that make sense? And what did we say about the frequency range over which the response of this chap must match the response of this chap? So, over what frequency range must these two magnitude responses match? Between 0 to omega p1. Over what frequency range do we care about? So we need this chap here to to approximate the first order system, all frequency ranges where the loop gain is greater than 1, because that's where we have feedback action. Once the loop gain falls much below 1, it hardly matters whether there is a match between this and the first order system or not, because at those frequencies the loop is completely dead, in the sense that the power amplifier gain is so low that it doesn't matter. And we made some calculation. In our example, what did we choose? 1 plus S by omega P1 the whole cube times S divided by omega P by 1000. Okay. So in this example, omega D is 1000 times smaller than omega P, and without having to go through the entire math, what do we expect for the maximum value of A0 F possible before sending the loop into instability? When omega D wasn't there, the maximum A0 F possible was 8. So now what do we expect? We'd expect that the maximum A0 F possible should be definitely larger than 8. How do we figure that out? We know that loop gain of j omega is nothing but A0 F divided by 1 plus j omega by omega P the whole cube times 1 plus j omega into 1000 by omega P. And we also saw that as we went on increasing A0 F, when A0 F was 0, all the poles will be at, but they were all minus 1. As we went on increasing A0 F, the poles, they start splitting, and then one set of poles started moving into the right half S plane, and precisely at A0 F equal to 8, we found that the poles sit on the j omega axis. So we can expect some similar kind of behavior here. So as we go on increasing A0 F, eventually the system will have poles in the right half plane. So somewhere the poles must cross from the left half plane into the right half plane, and the precise value of A0 F, which puts the poles exactly on the j omega axis, is the limit for stability. Does that make sense? So to find the limit of A0 F for stability, what we need to do is to find when Lg of j omega becomes equal to minus 1. And why does this make sense? When the poles are on the j omega axis, what is the closed loop transfer function? If the poles of the closed loop function, that is this guy here, if the poles of this closed loop transfer function in S, there is a pole pair on the j omega axis, then what can one say for V out of j omega by V in of j omega when evaluated at those poles on the j omega axis? This is the closed loop pole. So as I go on increasing A0 of F, at some point the poles will sit on the j omega axis. Let's call this j omega x, and this is minus j omega x. So if I now evaluate the closed loop transfer function at omega x, what should I get? The magnitude of the transfer function becomes infinite. Is that clear? If the magnitude of the transfer function becomes infinite, it is equivalent to the loop gain of the transfer function evaluated at j omega x becomes minus 1, because then the denominator will become 1 plus loop gain, which is 1 minus 1, which is 0. That's the motivation for this formula. Alright? The question is, what value of A0 F will result in loop gain of j omega x becoming equal to minus 1, and This is a complex number. So it has both a magnitude and a phase. So the phase of the loop gain of j omega is nothing but minus 3 tan inverse omega x by omega p minus tan inverse 1000 omega x by omega p. That's the phase. Must be equal to pi radians. One way of solving this, as I said, would be to push this guy on the other side. So 3 tan inverse omega x by omega p. Pi or minus pi is the same thing. Cancel off the minus. Make it all positive signs. And do this. Tan inverse omega x times 1000 by omega. Does it make sense? I could take a tangent on both sides. What is tan of pi minus tan inverse blah blah? Minus tan of tan inverse omega x, which is nothing but omega x into 1000 by omega p. So this becomes 3 tan of tan inverse omega x by omega p. 3 tan theta minus tan cube theta, which is basically tan of tan inverse x omega x by omega p divided by 3 tan square, and this must be equal to minus omega x times 1000 by omega p. So this is 3 omega x by omega p minus omega x by omega p the whole cube divided by 1 minus 3 omega x by omega p the whole square must be minus omega x into 1000 by omega p. Alright? And you can get rid of omega x by omega p as a common factor, and you will end up with 3 minus omega x by omega p the whole square must be equal to minus 1000 times 1 minus 3 omega x by omega p the whole square. You can go and solve this equation, and 3001 into omega x by omega p the whole square must become 1003, which means that omega x by omega p is approximately equal to 1 by root 3. Alright, so we beat into the math and got it. Last time around we found, intuitively we can see that the omega x at which this expression will have a phase of 180 degrees must be very far away from omega p by 1000, but must be smaller than omega p, which means that this factor will contribute 90 of those 180 degrees, and the other 90 degrees should be contributed by 3 of these poles sitting at omega p. If 90 degrees is contributed by the omega d, which is omega p by 1000, then each one of these poles at omega p must be contributing 30 degrees, which means that omega x must be approximately equal to omega p by root 3. From this equation you see that it is not exactly omega p by root 3 but slightly off. And now if you go and plug this in at omega p by root 3, that the phase of the loop gain function becomes equal to 180 degrees, which means that the loop gain of j omega x is a naught f divided by the magnitude of 1 plus j omega x by omega p. So that's root 3, and there is 1 plus j into 1000 by root 3, which is A naught F divided by one plus 1/3 whole cube times 1 plus 1000, and this is approximately 1000 by root 3, which means that the maximum A naught F possible is 1000 by root 3 times 4 by 3 whole to the power 3 by 2, and what is this approximately? 8? Approximately 890. If we didn't have omega d, the maximum A naught F you can tolerate before the system becomes unstable is barely 8. The moment we attempt to make this look like a first order system by putting a very, very low frequency pole, which is much, much lower than omega p, and in this example we chose something which is about 1000 times lower than omega p, and we see that the A naught F possible now before the system becomes unstable is increased about 100 times. So if I wanted to increase A naught F maximum to say 10 power 6, what would I have to do? I should decrease omega d, push omega d lower and lower and lower and lower until this happens. So this is with regard to a third order system which was fundamentally unstable, and we stabilized the closed loop system by introducing an omega d which is much smaller than omega p. So this omega d is called the dominant pole, because this pole frequency kind of dominates the other three, and this whole process of taking an unstable closed loop system and stabilizing it, frequency compensation, and this method of stabilizing the system or compensating the system is called dominant pole compensation. And what is the price we pay for dominant pole compensation? As you guys have guessed, if we plotted log omega and log magnitude of the loop gain, without compensation, our system looked like this. It had a slope of -3 on the log-log plot. This was log omega p. Then once we put in a dominant pole, what we found was the loop gain became and then beyond this point it will have a slope of 3. And where is omega d now? The frequency where the red curve starts to fall off, that is log omega d. And we know that you get all the benefits of negative feedback only when the magnitude of the loop gain is much larger than 1. In the uncompensated system, the magnitude of the loop gain remained A0F over a wide frequency range. Now, by deliberately pushing omega D low, you've lost out the magnitude of the loop gain over this wide frequency range here. So what was A0F will now start to fall off rapidly beyond omega D, and that's the price you pay. But you're gaining something. Earlier, with a large loop gain, you were not stable at all, so the system is useless. Now, you have stability, but the magnitude of the loop gain is reduced from A0F to something much lower as the frequency goes on increasing. And because it's so easy to do, it's very easy to introduce a pole at a low frequency, as we will see in a couple of minutes. Since it's very easy to do, it's very commonly done. However, this is by no means the only way in which you can stabilize the system. Somebody was pointing out, for example, that if you had a third order system, you could introduce zeros and poles. For example, compensation techniques, I will not get into the details, but I'll just give you a quick flavor for what's going on. This is the original system, A0F divided by 1 plus S by omega P, the whole cube. So if I now add another system whose response is 1 plus S by omega P, the whole square in the numerator, and 1 plus, say, S by omega P1 square, where omega P1 is much larger than omega P. This is the original amplifier. This is the transfer function of the so-called compensating network. So, if I cascade the two, what do I get now? A0F divided by 1 plus S by omega P times 1 plus S by omega P1 square So this is the transfer function of this a network which can be cascaded along with the forward amplifier. And please note that any network transfer function, it is not possible to introduce zeros without introducing poles. So the best you can do if you wanted to get rid of two of these guys is to, if you wanted to introduce two zeros, the compensating network must at least have two poles, correct? And so I have chosen omega P and omega P1, and as frequency tends to infinity, the best a network can have is a constant gain at infinite frequencies. It cannot have a gain which is increasing with frequency. The denominator is also chosen to be 1 plus S by omega P1 the whole square. So if omega P1 is much larger than omega P, when you multiply it out with the original transfer function of the forward amplifier, you get something of the form A naught F divided by 1 plus S by omega P times 1 plus S by omega P1 the whole square. Now since omega P1 is much larger than omega P, what does this approximate? If omega P1 is much larger than omega P, it kind of approximates a first order system with a pole at omega P. What happens now? When compared to dominant pole compensation, is this better or worse? Why is it better? Because the loop gain, magnitude of the loop gain remains A naught F over a range from 0 to omega P approximately rather than 0 to omega D earlier. You understand? But nothing in the world comes for free. So what do you think are the risks associated with such kind of a compensating scheme? See, whenever you are trying to cancel one effect with another, what you are cancelling must match what you are trying to cancel. The omega P's in the denominator here must exactly match the omega p is in the numerator here. If there is a mismatch between the two, there will be improper pole zero cancellation, which leads to basically a design which may not be very robust. While it is true that you get a larger loop gain over a wide range of frequencies, you must there now be very careful so as to location of the zero and the pole must be very, very close to each other, otherwise there is an issue. Such compensating techniques where you add zeros and poles goes by the name pole zero compensation. As I said, dominant pole compensation is very, very popular in most applications, and the reason is that as long as you ensure that the dominant pole is sufficiently below omega p1, it does not matter how low it is. If omega d is deliberately made 10,000 times lower than omega p, then whether it is 10,000 times lower or maybe 8,000 times lower, you're probably okay. So that is the discussion on compensation. Another couple of minor points I wish to add. These are basically related to intuition. We saw that the loop gain evaluated at J is -1. This is the limit for stable operation. And let's kind of quickly understand intuitively why this is so. So let's assume that I open the loop. So this is A of j omega, this is F, this is out, the earlier output terminal, and what we are doing is connecting the output of the feedback block to the input. Alright, this is how the loop is established. So, if I evaluate the loop gain of j omega is nothing but A of j omega times F. The loop gain evaluated at omega x is A of j omega x times F, and at omega x, if the loop gain is -1, what does it mean? If I cut open the loop, please note that for your reference I will again draw the loop. This is the loop. Please note that there is a negative inversion sign here. If A of j omega times F becomes equal to -1 at some particular j omega x, what does it mean? It means then that if I took this A of s and F and excited it by a sine wave with a frequency of exactly equal to omega x, what will be the steady state output here? Gain alpha at evaluated at j omega x is exactly equal to -1. Means that this becomes minus sine omega x times t. Correct? And how is the loop closed? I am taking this, multiplying this by -1, and then I would have connected it back to the input of A of s. That's what I would have done when I had to make my closed loop. Trying this thought experiment where I cut the loop open precisely at this point, and if I apply a sine wave exactly at a frequency omega x, what happens? At this frequency we know that the magnitude and phase of the loop gain are 1 and 180 degrees respectively. So the output of the loop will be minus sine omega x times t, which when you look at here will be what? Plus sine omega x t Now, if this guy is the same as this chap, then why do I need the sine wave to begin with? I can simply, the forward amplifier and F won't know if I just connected these two like this. You understand? So this is sine omega x times t. So what is this telling you? That this loop will support sustained oscillation at a frequency omega x, provided the loop gain or the gain of these two guys put together is -1. You understand? Yet another way of looking at it is to note that when you have a low frequency sine wave, when for example you had a very very low frequency sine wave, if I yank this up, what happens to this chap here? At very very low frequencies, much below any of the poles in the network, if this terminal goes up, what happens to this terminal? So if I cut the loop here, if I yank this up, this goes up, and because of the inversion this comes down, so there is negative feedback. If the loop gain satisfies this condition, where at a frequency omega x, if I put in a sine wave of j omega x here, alright, what comes back here is what? It's minus sine omega x. So after the inversion it becomes plus sine omega x. So you can see that what the phase shift has resulted in is that what was a negative feedback loop at low frequencies is now becoming positive feedback at omega x. Alright? And we saw how this loop, if the condition is satisfied, will basically sustain sinusoidal oscillations at a frequency omega x. Does that make sense? This is just a cheeky way of figuring out what the maximum limit on A0F is. A more rigorous foolproof way would be to write out the denominator polynomial of the closed loop system. Clearly the polynomial will be a function of A0F, and you can plot the locus of the roots as A0F keeps varying, and beyond a certain point the roots will get into the right half S plane and the closed loop system will be unstable. You understand? That is always the foolproof system of doing it. As it stands, loop gain of j omega x being equal to -1 will let you exactly identify the value of A0F, which will result in the poles being on the j omega axis. So to that extent this is also rigorous. However, the Nyquist plot and are the foolproof ways of figuring out what ranges of A0F will result in a stable closed loop system.